That's just, what is that for?
It looks like SQL logic to me, but I'm not sure. It's not something we've done.
Yeah.
Yeah. So yeah, it might be plus equals. It's typically C or Java.
I don't know much at all, but
Rating.
yeah, I think in Visual Basic,
Oh yeah, but that's not a real.
that's what I've heard.
No,
But it was fun to mess around with.
yeah, it is. You know, it's a good language to know because like this project that I'm working on for college, we're doing a visual basic, the VBA, and we've embedded it inside of an Excel spreadsheet.
Oh,
You'll see it. It's way cool. I mean, we just finished the project yesterday. Okay. So what we do is we go out, we run a query, and let me pull you up as a student so that I don't make like head on box. Okay. Okay. So what it does is it runs a query and it calculates your academic progress to see if you meet the federal stats for your Pell Grant. And to do this manually takes about 2 hours. Okay. Because we have to look at everything you've ever done and then semester by semester, what's your progression, how many did you attempt, how many did you pass, and then if you didn't pass it, how many did you put you in so you can keep your Pell status when you're earning scholarship. And it's kind of tricky, okay? So we can work on a program, and it's programmed in VBA in Excel. And when they ask me to write this code, I'm like, who's it done this for?
Yeah.
You know, I've written code in VB, but you know, it's really. And people who are Microsoft shops really accept me saying that. So.
Yeah. And this is something that it very. Oh, it seemed like it was kind of fun for me, but
It's a good
yeah.
one to learn. It's a good one to
Yeah.
learn. It's let me, because it's got a student in there, and I can do this. Okay, so what's your student? You know your student ID number?
046.
And I'm not on the.
Oh, I'm sorry. It's 046.
8. Okay, so what it does is it goes out and it runs a query off the state database and it builds your entire enrollment record, every class you ever take. Okay, that includes continuing ed and everything. And then this button says that quick, calculate your academic progress. Okay, so that takes about 4 hours for you. Okay, so
Yeah.
here's what the code
That's
looks
a lot
like.
of.
Yeah.
Right.
Yeah, so here's what the code looks like. And I had written macros in Excel, but everything like this, okay? So right here, it goes in, pulls on the data, it goes on these calculations, and it scrubs the data, gets it all nice and clean, organized, and then it does calculations of the practical progress. And and what's cool about doing this is,
Hi, can you guys hear us?
and I didn't know you could do this.
Hello?
Can you hear us?
And I was like, that's what it's about.
Yeah.
Okay.
I guess maybe.
It's very it's like summer. Okay.
Uh,
I like
you know,
wait for it to get colder.
or basic,
If I'm
ASP,
thinking during the day, like
all
your
those
average day yesterday was like 80 something.
Yeah.
Like I'm
ICT,
Mid-70s as the high. Like,
watch out on programs. That's probably this job. But it needs to be. And it's, but honestly, what to start.
I've heard
Okay. What?
Oh,
Something. You guys know how to do this? No, I've got.
That's something like this.
How's tomorrow?
Yes.
Here?
Yes. The hard part is the lodging.
What do you think about it?
Now, okay, should I add one?
What didn't even come from?
I know. I thought there wasn't
That's
one.
because
Okay, then maybe.
I'm thinking the else actually.
It's not 1.7.
I have 1.4. I'm
I
7, 8. Got 8 that I don't know what I'm doing.
I feel like any question on any problem would help me out quite a bit.
Hey, Mr. Garrett, let me go through every single question of the homework.
Can you do the
we have a nice one on class session
One on
at
class.
coffee house.
Just meet up with us.
Yeah. Listen to the Isothermal cup band that play the old jazz players.
I said, band.
We should do
that.
Risa said he would meet me in a minute. You see this? I'm fine. Yeah, okay. I didn't have time to eat breakfast, so I just grabbed a bag of carrots.
I was working out this morning. They're by South Davie, and at the four-way intersection there, the way I meant to go, there's a bunch of traffic stopped because of my bus, all the way up extending into the intersection, and I turned to the left to go, I guess, towards downtown Monksville. There's another bus that stopped the car right there.
Did you get the homework? Yeah, there's no 1.7.
For your
All of it? There's no 1.7. Alright, let me see.
You're just gonna have to test tomorrow whether it's 1.7 or not. I already cry every time reviews.
I can do.
I just hope my tears stay on.
Me last night, I was bent over the book like this. I don't understand.
See, I was sitting there and I was just like,
And my mom's just like, Freddie, are you okay? And she's like, I'm okay.
well, see, I told you how I was class and my dad's like, stuff like I told you so.
Chemistry grades dropped back from like a 99 to a 91.
Every time it was that, and then every time I ask, I'm like, I love that he tries to help, and he's like, I can't remember this. Let me research this and come back to you. He's up at 4 in the morning researching it for me, which is really nice, but then he comes up and I was like, Dad, I remember this so and I think I could. And he's like, it's okay. Now I know, so if you have any questions,
I'll show Alex.
But it's to the point where I don't know if I use the other
No, that makes sense. It was kind of, that does make sense, but that's not. And I showed him the first problem, and he's just like, Brittany, the word is 0. And it's just like, but, no, it's not, it's negative. I can't. It's just like, oh, I can't help you.
it's like, kind of thinks because I was on the negative, and I was like, that means -4 over x to the third. See, I don't know how to solve it for you. Like, I got that far. That's all I got.
Okay, so you got this. That's some misbehavior. I didn't know what's to say bad behavior the -4 wouldn't go under. Because it will bring it all to the site. Right? 55, 57, 53, 61, 73.
So let's go ahead and get started. I know it's like maybe a minute early, but I have to answer questions on some of that possible. Before we actually go over homework, let's just remind you that tomorrow we have a test on sections 1.4, 1.5, and 1.6. It covers continuity and then dealing with various types of limits. Limits going out to infinity, and limits going close to a number cancellation theorem, vertical asymptotes, horizontal asymptotes, things like that. All that was in there using limits. Bunch of limits for we can kind of do it. I put some kind of proof like we did, like that sine of theta over theta that we did yesterday. That's what's going to be for tomorrow. So we'll start today, open it up for questions on homework that you want to go over. Amy has her hand up, so does Brittany. Well, Sammy, you go first, I guess.
Sammy? Can we do 49?
Yes.
Oh, that's a good one.
Okay. I tell you what, let's just do this. So I'm going to write a little series. So, Sam's going 49. Brittany, what did you have?
41 and 47 and all the homework.
So, like, based on the odds, something? 41 and 47, you said?
Yeah.
That's what I added to the list.
51.
5, 3, and 29. Okay. We'll start there.
It's a metaphor. It is.
Question, please.
39.
39.
Did he just turn
So
yellow?
we'll just cover all of the odds. Start at the top, and all the odds.
It's an album cover, see?
Oh, yeah. Who has it? Oh,
Can we do 51?
again.
51?
5-1 or 6-1?
5-1.
6-1.
5.
Five.
You were holding
Hey,
it
so
up.
get your hand up.
Oh, no. Oh, right there. 59. 59 and 71.
Every single math problem.
Yeah. And I had like a really quick question about the methodology behind doing this. How
Okay.
much of it is just like common sense? Like when you think about this stuff? Like as this graph that's clearly gonna go negative, that's going to negative infinity. Like lots of this stuff I just thought about it rationally.
Well, that's true. But we want to do on this material, we want to do it algebraically rather than graphically.
Okay.
Does that make sense?
Yeah.
Yeah, graphically was the way we started with a lot of this. We're also now kind of transitioned to the algebraic. A graph doesn't hurt. If you want to look at the graph and say, oh, I got a sense of what this answer is going to be, there's nothing wrong with that. So, oh, look, the answer needs to come out to be negative infinity. But then you need to show how to achieve that algebraic. So, using a graph is not a bad way to start. Let's see. So, typical Carson's. Yeah, so we're back at. We'll see how many of these we can get. What do we have? 29. F of x equals 2 over 4 plus u to the negative 2x.
It's just 29.
Yes.
I'll see that. ABC.
Yeah.
See this? Okay. But what it asks us to find roots, discontinuities, asymptotes. Okay, Okay, so roots. What does that mean?
When y equals 0, what is the function?
Means f of x has to equal 0, which means that 2 over 4 plus e to the negative 2x has to equal 0, which doesn't happen. The only way that fraction is equal to 0 is if the numerator is equal to 0. The numerator is never going to be equal to 0 because the numerator is always 2. So no roots. Okay. What's next? Discontinuities. So when we look for discontinuities, what's a suspicion? When we talk discontinuities, we talked yesterday about suspicious points. So x values that could be a discontinuity is what we're looking for. And there's different ways that it can cause a discontinuity. We have jumps, we have removable holes, we have infinite asymptotes. So what do we look for? What's suspicious? Well, let's review. When would you see an infinite asymptote? This kind of discontinuity called vertical asymptote. When would you see that? What would be present in a function to cause that to happen?
Something in the denominator that causes it to equal 0.
The denominator is equal to 0 and the numerator is not equal to 0. That causes infinite discontinuity. Good. What about a removable discontinuity? Let's review that. What causes that?
A rural?
Removable.
Removable.
Immovable.
Removable.
Get back. I was down the dead zone. I got back on. Can you hear me better now? Removable.
It's like
Cause.
harder, I guess. Got it.
Well, problems to cover. We're spending a lot of time on something you're supposed to know here. Speak up.
Is he just talking about a hole? That's what a removable discontinuity is?
Yes, a hole is a removable discontinuity. That's correct. What do you see in a function that causes this hole, aka removable discontinuity?
A factor that gets canceled out on the numerator and the denominator?
Yes, if you have a factor that causes both the numerator and denominator to be 0, that's going to cause a removable discontinuity. That's correct. What about a jump discontinuity? Third kind. Here.
Talking about piecewise?
Limits are not going to be, the left and right side limits are not going to match up. What's the key way that we see that occur? What? You have what kind of function you have? If it's piecewise and they don't match up. So those are the 3 types of discontinuities we can discover in this function. Is this a piecewise function that can potentially change its position drastically at the drop of a hat? No, so it's not going to be a jump. That leaves removable and infinite discontinuities. And those involve, both times, division by a factor that causes 0. Either it's canceled at the top, causing a removable hole, or it's not canceled at the top, causing a vertical asymptote called an infinite discontinuity. So either case, we have to look at the denominator being 0. That means we want 4 plus e to the negative 2x equals 0. We clear how we got to there. I think the process should be fairly quick. I solved that. Whereas. Speak up, please. Grayson, did you say?
What did he say? What did he say?
He said solve it.
Solve it?
Grayson, did you have a suggestion?
No.
I thought somebody said something.
I think someone said bless you, but it's not really a suggestion.
Okay.
Me?
Well, I can use the blessings this morning, I guess.
Where does it? This is the part of the day where I just listen. It makes sense like 10 hours later. A natural log is the log.
Remember this from pre-calculus algebra?
Yes, it's been like a year, like literally a year.
Yeah, it's been longer than that since I took it. But yes, solve for x. I'm attempting to solve for x. When I do so, I have a log of -4, which is impossible. So apparently there isn't any discontinuities either. So none. Okay, what was next on the list?
Wait, so how does that prove all three discontinuities?
You can't solve that because you can't take it.
Well, once again, the way that we see a jump discontinuity is if the function rule literally changes drastically at some point in the domain. And the only way that happens is if you literally write a different function rule than the one we have now. So this function is a smooth continuous function. It's just going to do what it's going to do. It's not piecewise. So it's not going to be jumped. The other two functions, other two discontinuities require a division by 0. Since I cannot divide by 0 because I can't find an x to make that happen, then I'm not going to have either one of those discontinuities. Okay, asymptotes. How do we find asymptotes? We've eliminated one type of asymptote right here, did we not? Which kind of asymptote did we just eliminate? Why? Yes, to have a vertical asymptote, I have to have an infinite discontinuity. I don't have any discontinuity, so I can't have a vertical asymptote, period. So this also implies no vertical asymptote. Okay, so that leaves one thing that we've got to do. Horizontal asymptotes. So how do we look at horizontal asymptotes? Did this yesterday.
The coefficients of the top and the bottom. And then it depends on the degree as well.
Yes and no. That theorem from pre-calculus only applies if it's polynomial function in the numerator and polynomial function in the denominator.
Okay.
Is that what I have here? No, that theorem doesn't even apply. So what I did yesterday, if you recall, is I proved that theorem by doing an example so that you didn't have to just reference a theorem that you just kind of said amen to and didn't really understand. So how did we do that yesterday? Well, yes, we did. You're right. But before we got to that, what was the genesis that we were focused on? I said, this is how we're going to find our horizontal asymptote. Yes. Horizontal asymptote is all about end behavior. Turned in calculus. But end behavior requires what? X going to infinity. In fact, plus or minus infinity. So when x gets out large in one direction or the other, That's called the end behavior. Okay? The terminology you learned in pre-calculus was end behavior. You may not talk about x going plus minus infinity. You learned a parabola has end behavior going up or going down. Well, we can show that using limits. So horizontal asymptote is an end behavior phenomenon, and end behavior phenomenons require x going plus minus infinity. So we're going to look at limit x goes to infinity of 2 over 4 plus e to the negative 2x. And we're going to look at the limit x goes to negative infinity of 2 over 4 plus e to the negative 2x. Those two limits put together will determine the end behavior of this function. And if the end behavior is close to a constant number, then we'll say it has a horizontal asymptote. If the end behavior gets close to infinity or negative, then it doesn't have a horizontal asymptote. So if we can get this to come out to a constant number as a limit, then that means this function eventually starts to behave like that constant number. It's close to that constant number. Okay, so how do I do this limit? Do this limit. Yeah, that's exactly right. So this is,
Oh gosh, I'm sorry.
2 isn't affected by x going to infinity.
Yeah.
4 is not affected by x going to infinity. What do we do with this e to the negative 2x? Seems like we had a theorem about that yesterday. Okay, remember the theorem? Let's turn in our books to, yes, you're absolutely right. Look in your books on page 140. Page 140.
Oh. Yeah, that one.
Says, if k is greater than 0, then the limit k of x goes to infinity of e to the kx is equal to infinity, and limit x goes to infinity of e to the negative kx is equal to 0. We went over that yesterday. So here we go. I have, it looks to me like a negative 2x. That's a negative kx. So that limit right there better be 0. I can understand that better if you don't remember this theorem. It should be good if you did, but if you don't, Jacob had another suggestion. His suggestion is, well, let's do this as 1 over e to the 2. Agree with that?
Mm-hmm.
Negative exponent, you learned in pre-calculus, you magically put it in the bottom.
Yeah.
You know why you do that? Never mind. We won't go back to pre-calculus. There's a reason for that other than just I said so, but anyways. So it's just accepted small for, you know. In pre-calculus we talked about that. Anyways, so now what? Excuse me, I left off something. Limit x goes to infinity. I haven't actually applied my limit concept yet. All I've done is algebraically rewritten my expression so that maybe I can understand it better.
You can like the limit x approaches limit to x approaches anything like approximately 2 minutes.
Yes. So I can use my quotient rule. I can do the limit x approaches infinity of 2. I can do the limit x approaches infinity of 4. Then I can do the limit x approaches infinity of 1 over e to the 2x. And that should be fairly obvious now at this stage. So if x going to infinity, the 2 is not being affected. We said that a minute ago. That's just a constant. 4 is not being affected by x. And what is happening here? This is the part that we stumbled on initially. Now it ought to be more apparent. So when x gets close to infinity, e to the 2x gets really close to infinity because you're raising e, which is bigger than 1, to the power of 2 infinities. That's really big. So this is basically 1 over infinity.
That's like 0.
Oh,
I can't even see it.
can't see it. I'll have to pan back a little bit.
Oh, that's nice.
See now? So this tells me, this statement right here tells me on the right end behavior is horizontal asymptote at y equals 1/2. That's what I've discovered from that little bit of work. Well, what about the left end? Hence, horizontal asymptote does not have to be the same at both ends. Oftentimes it is, especially in pre-calculus, but it does not have to be. So the way we determine the left end behavior is we do negative. Go through the same process. Now, I follow the same plan, but this time it's going to mess me up if I'm not careful. Okay, so x going to negative infinity doesn't affect the 2, doesn't affect the 4. Those are just always 2 and always 4, so it doesn't matter what x is. But the next term, the last term in my fraction, is affected by x. And so x is getting close to negative infinity. What is that?
Negative 2 times.
And 2 times negative infinity. So it's getting close to e to the negative 2 infinities. I'll write that down and see if that makes sense. I'm just going to write e to the negative infinity. We'll agree that 2 times infinity is infinity still. So I got a negative infinity as the power of e. What does that mean? Wait, I'm sorry, that's not right. Apologize.
Oh my gosh.
1 over e to the negative infinity. I forgot my 1 over right there. Now follow that, I left out my 1. That changes everything. Apologize. Left out, there was a 1 over e to the 2x, so I should have 1 over e to the negative infinity right there. You understand why that should be 1 over e to the negative infinity? Everyone follow that?
Yeah.
Yeah.
Okay. So, now what do we got?
4 plus e to the infinity.
That's 1 e to the negative infinity is like putting 1 over e to the negative infinity. It's like making it e to the positive.
Wait, oh my gosh. Okay.
That's
Can you
like
repeat?
a little bit to the right. And then 4 plus, what is e to the infinity?
Infinity.
It's even more infinity.
Even more infinity.
And then that's 2 over infinity. What's 2 divided by infinity?
0.
So this tells me my left end behavior is horizontal asymptote at y equals
0. Okay.
Follow that now? Huh. Well, that's how hard it is on the very first problem on the list. I don't know what we're going to do for the rest of the list for. Hopefully that works. What's the next one? Any questions on that first? Follow that now?
Yes.
Okay, next one on the list is, looks like 39. We're just going to go through the list.
Wait, which?
If you run against something that looks very similar to what we've already done, we'll bypass. 39. This one doesn't have all that about roots and discontinuities. It just says calculate the limit. Okay, calculate the limit. Times x to the negative 4/3, x goes something.
Doesn't look like that.
Only 37. I apologize.
We can go home for any.
I can't count. Don't worry about it.
You're my math teacher.
Oh shit. I teach calculus. In calculus we don't count. We just yeah. But,
We just have
okay,
limits.
so
How close can I get to count?
Yeah, that's what you get.
okay. Well, that's, I mean, I want to enjoy a lab. Square root of x minus x. Is that right now? Did I get a copyright correct?
I was getting bad ad revenue.
What's copyright problem? What do we observe on this problem? You know, all we're asked to do is find the limit. So I don't have to worry about understanding anything about horizontal asymptotes, although you still need to know that. But on this problem, all I'm asked to do is find this limit.
Oh, that's great. I love it.
What techniques and skills have we learned about just doing limits? Let's just use our continuity theorem and see what happens. Okay, so we're going to plug in infinity for x. So what does that give me? If I use the continuity theorem, continuity of algebraic functions, I get square root of infinity minus infinity. Well, guess what, folks? Infinity is so large that even when you take the square root of it, it's still infinity. And that's an indeterminate form.
Dang it. That's indeterminate.
That's indeterminate. It's not necessarily zero. It might be zero, but it could be almost anything. So we have to have a different plan. A different plan. What plan have we often used, employed so far to deal with limits that come out indeterminate?
Cancellation, but that doesn't seem too smart
That's
here.
cancellation, but before you did cancellation, what did you have to do before you did cancellation? Brittany.
Can you
Did
plug
you hand
in a number for infinity?
I think you meant factor.
Well, no, infinity is a concept, so it's not going to be, you can't use an actual number. You have to just have a concept that I have this number that's bigger than the biggest number I can imagine. What we did before we canceled theorem is, Joe said, factor. We factor. Well, let's factor.
Oh, yeah.
Did you factor out of this?
Enlighten me.
Factor out an x, I heard, or something. Whatever you want. You want to factor out an x? Factor out x.
Yeah, do
Does
it.
that leave it?
I don't know
To
how
the
to
1
factor
to the
it.
1/2 power.
What, cube root or something? What you want?
Would it be 1 to the 1/2 power?
1 to the 1/2.
Because that's the same as the square root of 1 when you take out the x. Or you could just put 1.
What?
If you multiply the square root of x by something that's divided by the square root of x, then you're just going to get the square root of Right?
What?
Right? Well, both by x. Okay, just kill me. Go ahead. I'll just take it.
Do we all agree that x is equal to the square root of x squared?
Yeah.
So if I have a square root of x, and I don't know, that seems to be like if I divide that by the square root of x, and then I just get square root of x, right?
Gosh. Yeah. Yeah.
Or if you want to put it in exponent form, use exponents half power will work. But this is a half power. Back out of 1 power, you've got left the negative 1/2 power, which is in the denominator. However y'all want to do it. Back. I chose X because Justin said X. So I could back it out of square root of X if I wanted, whatever. So what does this mean?
Well, you want to do the constant multiple thingy, or you put the...
Yes, no, be careful. There's not a constant multiple here. It's just an X multiplier, but I can use the product. So this will be the limit X goes to infinity of X times the limit X goes to infinity of 1 over the square root of X minus 1. Product rule.
Okay.
Okay, good. What's that? Yeah, okay, now what?
Well, you want to put infinity in, right?
Yes, we want to actually try to plug in infinity. So I get an infinity there, okay, times. So far, so good. So I get over here. Yeah. I'll show all the work, but yes, Jacob, you're right. So
That's basically 0 minus 1.
yeah, basically 0. If you agree again that infinity is so large that the square root of infinity is still infinity, then 1 divided by infinity is 0.
And infinity times negative 1 is negative infinity. That's it. Yeah.
What's your limit?
Yeah. I had a question about this question.
Good.
So what I meant by like having an understanding of what the graph would look like is like I thought about for any value of x, if you plugged it into that thing and it got bigger, right? Like subtracting x from the square root of x, it would always get to a bigger negative value. So I kind of just presumed it was negative infinity, right?
That's a good intuitive understanding, yes. That when we had infinity minus infinity right here, we did this initial continuity attempt. Here's what this said. The infinity that you're subtracting is bigger than the infinity you're subtracting from.
Yeah, because it's a square root of it.
So it's, even though they're both going to infinity, this infinity is getting there faster. It's got more power, if you will, than that one. So it's going to overcome it and make it negative infinity.
So would you...
That's exactly a good gut feel of what's going on, but you still need to show the algebra what's happening.
Okay. Okay. Curses.
Okay, what's next? 41. Moving right along. We've got 2 problems left.
Got him. Is what I live for. Calculus in the morning. Get a bagel every day.
41. Calculate this thing. Okay, well this is going to be kind of like that one, I think. So maybe we don't have to do the whole thing.
I can't even see. I'll let him realize it. I'm the only one that keeps on talking, and then it becomes obnoxious if I'm the one that keeps on talking. Yeah, but I kind of want to understand this.
Well, you want to understand, but you also seem to not be able to handle quiet space either. That's the thought.
I would hope we could actually see the board.
Can you move the camera up, please?
Thanks, guys.
So when we attempt this limit, if we attempt it, again, to me, when I see that limit, I see the same thing as here. The same thing as here? I'm like, oh no, that's got square roots. Okay. Well, if you attempt to plug in, what do you see happen? what's going to happen in this first term?
Negative infinity.
Negative infinity. What's going to happen in the second term?
Plus infinity. Plus 11.
But who cares about what? So, infinity minus infinity. That's indeterminate. So we got to do something else besides that. What are we going to do?
Infinitely smaller.
We're going to factor. I count next to the fifth. And you're almost done. You factor on next to the fifth.
I remember this.
Now what do you see? You split it up by product rule, you're going to have a infinity here times, what's all this coming to? Negative 3 plus 0 plus 0, which is negative 3. Negative 3 times infinity is negative infinity. We all see that that's dot, 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 when it works, negative infinity.
Negative 3 plus 0 plus 0.
Oh, that's the same thing? Okay. Sort of. Pretty simple.
I'll just look at it later.
Infinity times negative 3 plus 0.
Infinity times negative 3. Okay.
You see it without the work? I mean, I'm assuming it looks to me just like that. You all see it looks just like that?
I don't see what's on there, but
Infinity times what's going on in here turns out to be a negative 3 by the same thinking we went through over there. So that's the same problem. 47 is a little bit different finally. So x goes to 0, x over x squared minus. Okay, so what do you think about this one? What's the first thing you want to try?
X times 1 or x squared minus x.
Oh, okay, so you made it a product. I got you. That's what I was going to suggest. First thing is, just try plugging in, see if it works. It does it, you get 0 divided by 0, so it's an indeterminate form, 0 divided by 0. Again, I would encourage you to try that first off because you might run into one that you don't have to spend a lot of time doing all this extra algebra and just get the answer. This one doesn't, so I'm going to try something. I'm going to suggest, you could do what Jacob suggests, which is split it into a product, and that's fine. But maybe this time we have a hole in the graph, possibly, like we've seen before. If we factor, we can actually apply the cancellation theorem. So we haven't used the cancellation theorem. So this one I think is going to be a cancellation theorem. So you can have x times 1, I guess, over x times x minus 1. Then if x is not 0, then we can cancel these x's out of here. How do we know x is not 0?
Because it's getting close to 0.
We can apply the cancellation theorem. If x is not equal to 0, how do we know x is not going to be 0 to allow us to cancel that?
Because the function is approaching 0 because that's our c value.
Yes, we're approaching 0, but it's not going to hit 0. It's just getting close. And so now we're ready to say, well, this is 1 over 0 minus 1, which is 1.
so you,
Okay. No, we're picking up pace. That's good. 49. Over here, that's 49. 49 says, let's 3x plus 1 squared. And x goes to infinity of 3x plus 1 quantity squared. What's the name of that? 1 minus what? Okay. If you just try to plug in infinity into that, what do you observe?
Infinity.
Infinity squared times infinity, which is like infinity cubed. Here you got an infinity cubed, so we've got infinity cubed over negative infinity cubed. That's indeterminate. And then infinity over negative infinity, which is indeterminate. Okay, so what are we going to do next? Well, the 1 minus x cubed can factor. If you see that, you'll see that 1 minus x cubed is a difference of cubes and could factor. The thing is that a problem? Is that causing like an asymptote, like right here? Is it a problem like we had here, where you're going to have this cancellation that's going to help you in any way? Even if you cancel out, cancel this factor. So if I factor this, you get 1 minus x times x squared, 1 plus x plus x squared. I can factor a minus sign out of that and make it minus of x minus 1. And now this x minus 1 and that x minus 1 are canceling. But folks, you still got, that didn't really hurt you because that wasn't a 0 in the denominator. We're putting an infinity in there. So since I'm not getting a 0 in the denominator, which is going to cause a problem like here, then I don't need to go through all that extra work. I can just say, well, who cares? It's not a 0, so I don't have to worry about it. What else can I do? Well, another simple trick is, like we did yesterday, let's factor out the highest power. So in order to do that, let's distribute it and get it out into highest power. So what does this come out to be if you distribute it out? 9x squared. 1 times x minus 1 over 1 minus x cubed. Let's distribute again. The 9x cubed minus 9x squared plus 6x squared is minus 3x squared. 1x minus 6x minus 5x minus 1 over 1 minus 6.
Can you zoom in on that a little?
Is that better now?
Yes.
Okay, so if you still attempt to plug infinity, you're going to get infinities up here. In fact, in the numerator, you're going to get infinity minus infinity, which is not good. And then over infinity, so we're still at an indeterminate stage, but with infinity over infinity, like we've seen, one way to handle it is, and the most common way and probably the easiest way, is just to factor out. So we'll factor out an x cubed. And once again, as long as, I'm just going to stick up here, as long as x is not 0, we can cancel that. And since x is going to infinity, then it's not going to be anywhere close to 0. So we can say that this is I minus 3 over x minus 5 over x squared minus 1 over x cubed over x cubed minus 1. If x not equal to 0, we can cancel. And it's not 0, this time not because we're just approaching 0, but because we're not anywhere close to 0. Now when x approaches infinity, if you split it up into numerator and denominator like we did before, and do individual terms, what do you see happening now? We'll follow that, how we got all those zeros in there? How did we get 0? Divided by infinity. That's correct. Into a constant. Infinity divided into a constant number gets close to 0. Okay, what's next? Oh, okay. Good. Here. So we just did which one?
49.
We're on 49 now? So we're at 51 next? 51. Okay, 51 now. Limit x approaches 0 from the right of x to the negative 1/3 minus x to the negative 1/3. What's your first attempt? Plug in 0. What happens? Plug in 0. Infinity minus infinity. Does everyone see this? If you don't see it, let's rewrite it real quick so you can see it more easily. You rewrite this, if you decide to, you rewrite this as 1 over x to the 1/3 minus 1 over x to the 1/2. And now if you plug in 0, you're going to get infinity minus infinity because you're going to get 1 over 0 and 1 over 0 on the right. So let's do that. Just do 1 over 0 from the right minus 1 over 0 from the right, which is infinity. Okay, so what can we do then? What can we do? Factor. We're getting, see, we're on it now. It's factor. Okay, good. So what are we going to factor out? I'm going to go back up to here and do my factoring. Does that feel like it? It's easier for me if I do it that way.
I'll take it. It's gonna be an X.
Take out the biggest power, I think, is usually what we kind of go with. What's the biggest power here?
Negative 1/2.
The biggest power is negative 1/3, is it?
I don't know, man.
Negative 1/3 is to the right of negative 1/2, so it would make it bigger. Right?
Oh, yeah. So
Sammy,
1/3 is
explain.
less than 1/2, but since they're negatives, it'd be bigger.
Okay.
Negative 1/3 power is a bigger power than negative 1/2.
Yeah. Okay.
What power do we get now?
Gosh. What is it? What is that? Is that a...
Negative 1/6.
Negative 1/6 power?
Because you multiply that or something?
How did that happen?
How did I get negative 1/6 power? Okay, how do we factor? So let's see. When you factor, you're dividing out. So if I have x to the 5th plus x to the 4th, and you factor out an x to the 5th, what you're really doing is multiplying by x to the 5th over x to the 5th.
Mm-hmm.
Okay? Multiplying by 1. You don't do this in 8th grade. You just say, let's do something, but it's all magic. But here we're going to do x to the 5th, and then we're going to have x to the 5th plus x to the 4th over x to the 5th. And so that means I'm going to have to subtract exponents. So this is going to be x to the 5 minus 5 is 0, and then 4 minus 5 is what, x to the minus 1 or something like that? Same idea here. If I'm factoring out an x to the negative 1/3, then I'm doing the same thing. So x to the negative 1/3 over x to the negative 1/3 times x to the negative 1/3 minus x to the negative 1/2. That gives me an x to the negative 1/3 times x to the negative 1/3 minus x to the negative 1/2 over x to the negative. And that gives me x to the negative 1/3 times 1 minus. Now you got to subtract those exponents. Negative 1/3 minus negative 1/3 is x to the 0, so I'll rewrite that x to the 0. This is x to the negative 1/3 minus, excuse me, negative 1/2 minus negative 1/3 is negative 3/6 minus the negative 2/6, which is negative 1/6. Okay.
Okay. I'll just take a picture of that later. What time is it?
Can read that? I can't read it. That's I knew what I was talking about. Did you follow all that? The problem with factoring, if I just take out the biggest powers, it gets a little confusing when you get fractional exponents, negative exponents. But if you understand what you're really doing, you do the same thing no matter what. Okay, so what do we have here now? This is 1 over 0 plus, like we saw a moment ago. This is 1 over 0 plus times. I got to do the limit of this one, so I'm splitting my limit up into 2 pieces. I'll even show that again. So I've got a product rule, so I'm going to do limit x approaches 0 from the right of x to the negative 1/3 times limit x approaches 0 from the right of 1 minus x to the negative 1/6. This is 1 over 0 plus times, and this is 1 minus 1 over 0 plus. Let me calculate. Are we with me here? Yeah. What is 1 over 0 plus? Times, what do we get here? 1 minus infinity, which is negative infinity. And infinity times negative infinity is actually negative infinity. Okay, that was 51, so we're all the way to 65. We might get probably. Oh my gosh, we got logarithms involved. They can't be serious about that, can they?
Well, they are, apparently.
Okay, 65. 65. Limit. X goes to infinity. Make sure I copyright wrong. Logarithm of x squared minus logarithm of 2x plus 1. Well, I can see what's going to happen here, I think. Maybe. So if I first try my continuity theorems, what do you observe happens? You plug infinity into x and square it, you get infinity. And the logarithm of infinity is infinity. Justin said that's right. And then same thing here, plug in an infinity, you get 2 times infinity, that's infinity. The logarithm is still infinity, so that's indeterminate. Now, normally the game is let's factor. But is there anything common I can actually factor here? No, because I've got stuff inside the logarithms, so I can't factor that outside the logarithm. But if I use a property of logarithms from pre-calculus, and Justin said, well, I could rewrite this as a logarithm of x squared over 2x plus 1 by simple algebra. And now I can make this easy because I can use the composition theorem we discussed. You have function of a function. You can pull the outer function outside the limit type of game. So this is a logarithm of the limit x goes to infinity of x squared over 2x plus 1.
That's cute.
That's, once again, just putting down what we're doing. This is just algebra. This is composition theorem. That we've discussed. Now it's easy, I think. Well, it's easy.
Yeah.
How are we going to do it? We got infinity over infinity. Y'all with me? This is going to be infinity over infinity. That's still indeterminate. I got to do something different. Right. Factor out an x. That's a good idea.
Yeah.
Do that.
That's smart.
Sure.
It's real smart.
So logarithm limit x approaches infinity. You want to just factor an x like this to x times. Is this what you meant? Just I'm not sure. Let's make sure I know what you want. Is this what you wanted? I thought it was probably a good idea. But if not, well, that's still infinity over infinity, isn't it? It's still got x. You like how the bottom so so let's factor x out of the top and the bottom.
Alright.
This would be 2 plus 1 over x. I'll agree with that. Sure, that works. So now those x's can cancel because we're not anywhere close to 0. So this is just algebra again. So this logarithm of the limit x goes to infinity of x over 2 plus 1 over x. Because we can use the cancellation theorem if x is not 0 when it's not 0 because we're close to 0. And then we can go over here and we've got the logarithm of, so now we can actually start trying to plug in one more time. If I let x go to infinity, in the numerator I got a infinity. Denominator I have a 2 plus 1 over infinity, which is the logarithm of infinity divided by 2. It's 1 over infinity is 0, which is still the logarithm of infinity. Half of infinity is still infinity, and that's infinity.
Great.
Okay. Which one's next? Let's see if we can get through all these real quick. 71 was next. Oh my gosh.
Oh my god.
9 squared of 3x. Okay. Well, let's go here. Okay. Limit. What is it? X goes to 0.
Yeah.
9 squared of 3x. What? X cubed minus 3x? Minus x.
Yep.
X minus x. Okay. Punch. Punch. I see something kind of vaguely similar to something we talked about yesterday, but it's not exactly. maybe we can manage it and try to get it to look like it. Remember that proof we went over yesterday, the sine of theta over theta as theta goes to 0 is 1?
Yes.
To me, that looks vaguely similar to and then x goes to 0, sine of x over x equals 1. So if I can maybe somehow make that work out, that would be nice. I could then leverage that theorem to make my work easier. Okay, so how can I do that? Any suggestions? Here's my first hint. You have a suggestion? Go ahead, Joe. Yeah, exactly. I want to factor an x squared out of the denominator. Why? Well, because I got a sine squared. That way I can have the square of that thing over there, in a sense. You know where this is? So I can rewrite this as sine of 3x times the sine of 3x over x times x times, I factor out an x squared, then I got an x minus 1 over x. So far, so good? Now we'll use the product rule, I guess. Let's see. So limit x goes to 0 of sine of 3x over x times the limit. In fact, we got the square of that, so I'm just going to square that whole thing. We got two of those, so I'm just going to square that. And times the limit x goes to 0 of 1 over x minus 1. Are we with us to there? So I took these two things here are the square of sine of 3x over x. And so because it's the square of it, I can take that outside limit. So maybe I should have done that in 2 steps. Maybe that was confusing. Let's do it in 2 steps. Okay, there we go. Now I can rewrite this one like I had a moment ago. It's not quite exactly like it's supposed to be over there. Remember the problem we ran into yesterday where we had to put in an extra factor and change our, remember that? So if I play that game real quick, I could multiply, for example, by 3 over 3 here. And what does that give me? Three times the limit, x goes to 0, of sine 3x over 3x squared times the limit, x goes to 0, of 1 over x minus 1 over x. As we saw yesterday, we can make a variable substitution right here. We observe that x is going to 0, but we've got a sine of 3x, so we really kind of need a 3x idea. So if we let w equal 3x, then observe we've got x going to 0, but as x goes to 0, then 3x must go to 0, so w goes to 0. So I can replace x goes to 0 with w goes to 0, and I can replace 3x by a w, so I get this 3 times the limit w goes to 0 on sine of w over w squared times the limit x goes to 0 of 1 over 1 minus 1 over x. No, it's good. X minus. Now we're about done. So this is 3 times 1 squared times what do we get over here? 1 over 0 minus 1 over 0.
Okay.
Yeah. And this is 9 times 1 over negative infinity, which is 0. 9 times 0, which is 0. I have one last problem, I think, on the list, 73. Let's see if we can, we're out of time. Let me just mention to you real quick. So 73, what is that? On 73, it's going to be similar to what we just went through. Cosecant, remember cosecant is 1 over sine?
Yeah.
But you've got a 1 over sine involved, so if it's a sine in the denominator, you've got a x squared in the numerator. So one of those x's with the sign in the denominator can be used with this theorem. The other x in the numerator with the 1 minus cosine of x in the denominator, cosine of 2x, can be used with the other theorem. We had another theorem for cosine. So you can manipulate those in a similar fashion we just did and get one factor will be involving sine of x over x. If they're reciprocal, so you're going to have a negative 1 exponent. And the other one will be 1 minus cosine of x over x reciprocal. And you put those together and get the answers from the factors. Okay. That's all we have time for today, I guess. So we'll plan the test game tomorrow the same. We'll start early.
Mr. Gaddis.
Oh, I'll hang around for a few minutes for extra questions. If anybody needs to leave, please do. I know some have to leave. If you have extra questions, I'll hang around. Raise any other questions.
Are we gonna have a calculator tomorrow?
Yes.
And is it also another alone test?
Oh, alone. I'm sorry. I misunderstood. I thought you said, is it a long test? No. Yeah, all the tests are long. But, it is not an alone test. It is an individual test. I mean, it is an alone test. It is an individual test. It is not a group test.
Okay.
In fact, I would count on all my tests from henceforth being individual tests. The group test was the first time simply because 2 reasons. One, we needed to be experienced with the type of test and level of the test, but it was pre-calculated, so it was reviewed. So I saw it as being an opportunity to try out a test in a group format without the pressure of doing it individually. Any other quick questions? Again, if you have questions, I'll hang around for a minute. That's no problem. No. We have questions?
15 minutes early thing again?
No, wait.
We're like 15 minutes late with a late club. Okay.
The late clock. You started 8, ended at 15 late.
I'll be here early. Breakfast in the morning.
I guess we're good. Amanda, I'll send you tests later.
Okay.
It was this, like,
Like an hour later.
this is like
How do you decide that?
It's supposed to be E.
Limits. You say, well, look, limits are doing this. So it's
That works.
it's an infinite discontinuity. You have to look at discontinuity. You have to look at just finding limits. Create finding.
Scheduled.
Discontinuity is involved with it, so you're always doing limits. Just limits plus continuity. Good question. No,
Derivatives and.
we're going to hit derivatives soon, like the next chapter, and that's
Some type of
fine.
substitute.
So if you recall when we started the class, we looked at Galileo's bowling ball, and we found the speed of that bowling ball right as it hit ground. That was involving a limit, and that speed can be defined as a function using limits, so that I don't have to go to the table every time. I can.
And then this one would be 3
Student
over.
enumerate answer for a limit. I can actually create a function from a limit. That will be where we go next. So we need to understand limits before we can create that.
And school supplies are not on sale any longer.
I know. And the bad thing is, I bought like a ton of notebooks, and we have a ton of notebooks. But by the end of this semester, I am not gonna have a ton of notebooks. I'm gonna have 0 notebooks.
I think they're still on sale at Walmart. You should go by there. They're actually like clearance at Walmart. They were last weekend.
I'm gonna go stock up. I got one subject notebook.
Yeah, you're gonna need more than that.
I don't know why.
Do you think?
I feel like I understand.
And I was looking over those also for like 6 hours. I mean, I haven't seen the test, but there seems to have always been one of those. Yeah. I mean, I really like the idea of always doing 3 sections at a time and collecting calculations. Because when I took it, it was a midterm and a final.
Yeah. I mean, I'm glad about that.
I wish we had more time to slow down.
But, oh well.
Oh, I
It
need
is.
to.
Because it's like if you don't understand one day, we're already on a different thing the next day, so.
I mean, he seems to be answering all of your questions. So.
It's just too bad I have so many questions that we can't answer in the amount of time for a class. Yes.
0 over 0,
Like-
1 over.
That sucked.
Don't you feel better about it now, though?
A little. When does he get 1 over 0?
I mean, if I get this and squeeze, I think I'll be okay.
Wait, the 0 plus is 0 from the right.
Squeeze is still getting me geeked. You know,
You can take something and just say 1 over
I'm with
0.
you know, Lx is less than f of x is less than ux.
But as long as you get those 2 sides to be the same number, then the middle's the same number.
Yeah, I know, but it seems kind of arbitrary to me. A lot of this stuff seems arbitrary, but I just follow through with it.
I mean, basically, you're now at the point where you learned all this stuff, and now it's like, why did I need to know that stuff? Because now you have to show that you know all this stuff.
And I wish I could just
And
go-
from now on, it'll be showing everything that you know. Especially when you get up to real analysis. And
Yeah,
But what if I don't remember everything that I learned?
well, you gotta remember it.
when you get to real analysis, it's all proofs. Like in grad school, all I did was write paragraph-long proofs.
Yeah.
That's
not going to
Does not sound fun.
What class would we be doing that?
I guess any higher mathematics, right?
Lots of undergrad classes do real analysis, but since my undergrad didn't have real analysis, I had to go back and take the undergrad class in my grad school.
So if we're taking calculus 2, 3, and 4.
And I took it with the guy that wrote the textbook, and it was
Yeah.
super hard.
It's like Spanish, but with
This is
numbers.
more like Greek.
Yeah. That was clever.
Well, I looked at it and I was like, man.
I wish Dale would have heard your comment about
Which one?
we're just getting close to counting.
Oh, yeah. I wish he did. There's so many jokes that he's missing. He missed my album titles for the Isothermal cover band.
You and Dale would get along well.
The Gladiator.
Similar sense of humor.
Or
I think they are a lot easier.
I hope.
I mean, they're all based on limits, but
Yeah. If
Wait,
we ever
what's
go to the
his
math
word?
competition, we meet
Derivatives.
Yale. We should just go like a stand-up comedy show with Dale.